Hello everybody. So in the last video, we defined convergence of an infinite series. We said that an infinite series converges if the partial sums, which are the first sum of the first n terms, converge as a sequence, and otherwise it diverges. And all the strategies we had in that section were dependent on finding the partial sums, simplifying the formula for the partial sums, and then taking a limit of it. But unfortunately, that can be quite difficult in general. So it's nice to have some tools to decide if a series will converge or not without actually being able to explicitly calculate everything. So let's get started. And maybe a first remark to be aware of is that if a sum converges, then the individual terms an have to go to 0. So this is useful to keep in mind, right? If we're going to sum up infinitely many things, and we hope that it's going to converge to something finite, then we would expect that the individual terms have to be getting smaller and smaller, right? If we are summing up a bunch of things that are still large, then it's going to probably go to infinity or minus infinity. But maybe even more useful than this is a so-called test for divergence that we get by turning this around. So we said that if the sum converges, then the terms go to 0. So it follows that if the terms don't go to 0, then the sum cannot converge. Okay, or another way of writing that is to say that if the limit of the terms does not exist, or if the limit of the terms is non-zero, then the series diverges. Okay, so this is a useful test called the test for divergence. You just look at your series. If you see the terms aren't going to 0, you can say straight away the series does not converge. For instance, the sum of sine n diverges because we see the terms, the individual terms are sine n. Sine n does not go to 0 as n goes to infinity. Same story with the sum, say, of 5n squared over 5n squared plus 4. Right, if you think about the sequence n squared over 5n squared plus 4 divides up and bottom by n squared, it's going to go to 1 over 5, which is not 0. Okay, so the sum cannot converge. It's as easy as that. But let me say one thing here. This is a test for divergence. It is not a test for convergence. If the terms go to 0, that is not enough to say that the series converges. So this is a huge mistake that people make very, very often. So please be very careful. If the terms go to 0, that does not imply that the sum converges. What we can say is if the terms don't go to 0, then the sum diverges. But that's very different to what we said here. Okay, so if I said that I should give you an example, right? If I'm telling you terms going to 0 is not enough for the series to diverge, then I should give you an example of why that's true. So I claim that this so-called harmonic series, so this is a very important series to be aware of. The harmonic series, which is the sum of 1 over n, so that's 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on. I claim that this diverges. And there is a trick that I'd like to point out. So what is a trick? So what did it mean for a series to diverge? It meant that the partial sums diverge, right? Every question about a series is just really a question about the partial sums, which is the sum of the first n terms as a sequence. So we have to think about the partial sum sequence as n. And let's calculate a couple of special cases. So I can't hope to simplify the partial sums all the time, but let's try to at least understand a couple of cases. So I'm going to pick them out specially and see what happens. So S2, it's the sum of the first two terms. That's 1 over 1 plus 1 over 2. S4, it's the sum of the first four terms. So that's 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. And then here I'm going to make an inequality that I'm going to keep the first piece, but then the 1 over 3, the 1 over 4, I don't like it, it's complicated. And I'm trying to show that my series diverges. So I want to show that my sequence of partial sums is bigger than something that's going to diverge. So I want to come up with some estimates for the Sn, for the different partial sums that I'm calculating, to show that they are bigger than something which itself is going to be big. So I want to say that 1 over 3 plus 1 over 4 is bigger than 1 over 4 plus 1 over 4. So I'm saying that 1 over 3 is bigger than 1 over 4. Okay, that makes sense. 1 over 3 is 0.33, 1 over 4 is 0.25, that is true. Right, I can make a fraction smaller by making the bottom bigger, which is all I did here. And now the advantage of having 1 over 4 plus 1 over 4 is that simplifies nicely to 1 over 2. And now I have 1 plus 1 over 2 plus 1 over 2. I have 1 plus 2 over 2. And why did I do this? Why am I writing this in this funny form? It's because in a second we're going to see a pattern. So just it is what it is for the moment. Next, let's go to S8. Why did I do S8? Because it fits the pattern. There's going to be a pattern in a second. For now, just take it as given. So S8 is the sum of the first 8 terms, plus a third, plus a quarter, plus a fifth, a sixth, a seventh, and an eighth. And then we saw how to handle the third plus a quarter a moment ago, right? We replaced that by a quarter plus a quarter. It was bigger than a quarter plus a quarter, which was a half. And then a fifth plus a sixth plus a seventh plus an eighth, that's a mess. We want to be able to estimate it below by something we can actually calculate. Okay, we're trying to make it smaller. We're trying to prove it's bigger than something. Let's make it smaller. That means we can make the bottom of the fractions bigger. That will make the fraction smaller. Okay, so 1 over 5 is bigger than 1 over 8. 1 over 6 is bigger than 1 over 8. 1 over 7 is bigger than 1 over 8. Of course, 1 over 8 equals 1 over 8. And now we have 4 copies of 1 over 8. So that's going to be equal to 4 over 8, which is a half. Okay, so in the end, we proved that this next 4 terms, the new 4 terms that we got, was bigger than 4 copies of 1 over 8, which is equal to 1 half. So now we've managed to show that S8, the sum of the first 8 terms, is bigger than 1 plus a half plus a half plus a half. So now we have 1 plus 3 copies of a half. So 1 plus 3 over 2. Okay, so let's see the pattern. We had S2 is 1 plus 1 over 2. S4 is 1 plus 2 over 2. S8 is 1 plus 3 over 2. Each time I double the number of terms I'm saying, I have 1 plus an extra 1 divided by 2 with the estimate. So S16, if I double the number of terms again, I get 1 plus 4 divided by 2. You could check. There's a lot of writing, but the new term we get another bunch of terms, 1 over 9 plus 1 over 10 up to 1 over 16. That together will be bigger than a half if you estimate them all from below by 1 over 16. Okay, if you do this pattern, you'll see that S 2 to the n, so if we sum up 2 to the n terms, it's going to be bigger than 1 plus n over 2. And of course, here as n gets bigger, n over 2 is going to go to infinity. So 1 plus n over 2 also goes to infinity. Okay, so we have that the partial sums, the sums of the first n terms, they're getting bigger and bigger. In particular, some of them are going to infinity, and it's increasing, so the partial sums are going to infinity. Okay, so that proves that the harmonic series diverges. So that's a very important series that you should be aware of. The sum of 1 over n diverges. Please don't be tempted to say that 1 over n goes to 0, so the series diverges. 1 over n goes to 0, but the series, sorry, don't be tempted to say 1 over n goes to 0, so the series converges. 1 over n goes to 0, but the series diverges. Okay, so that's important to be aware of. Okay, next up, just something you would expect. If we have 2 convergent series, we can combine them by adding and multiplying by constants and so on. If the sum of an converges, the sum of bn converges, and c is a constant, then the constant multiple of an converges and an plus bn or an minus bn converge. The sum of a constant times an, we just pull the constant out, just like with integrals. The sum of an plus bn, we just split the sum. It's the sum of an plus the sum of bn. So nothing you'd find too surprising. For instance, we saw in the last video that the sum of 1 over n times n plus 1 equals 1 by using partial fractions and telescoping. It's easy to check the sum of 1 over 2 to the n equals 1. For instance, it's geometric with common ratio r. This is just a half to the n. R equals a half, rather, and first term 1 half. Okay, so if we were to calculate, for instance, 3 over n plus 1 minus 1 over 2 to the n. Okay, 1 over n plus 1, the sum is 1. So 3 over n plus 1, the sum is 3 times 1. So 3. And then the sum of 1 over 2 to the n we said is 1. Okay, if we subtract them, it's just we just subtract the sums. We get 3 minus 1, which is equal to 2. Okay, so that wraps it up for this video. So we had the very important test for divergence. If the terms do not go to 0, then the series diverges. But we said that if the terms do go to 0, that is not enough to say the series converges. The series might diverge or it might converge. It just depends. And one important example we saw was the harmonic series, the sum of 1 over n. We said that 1 over n, the individual terms go to 0, but the sum of 1 over n diverges, and we had a nice little argument for that. And then we had just a way of combining series that we already know converge in the usual way that you would expect, kind of a limit loss for series kind of thing. Okay, thanks everyone.